Good morning, everybody. It's Friday morning. The weekend is soon upon us, and it's just a little more than 1 week left to Christmas. But we have a little gift for you today as well, in the shape and form of Andreas Fall, who is going to round up this week of short webinars on the theme of scaling up bio-based materials. And we have a good one for you today. It's on nano graphite papers, which have great potential for future applications in various ways. And it's a matter of both research and scaling up, which Andreas will present to us now. And I would like to inform you briefly that this seminar is recorded. Link to the recording afterwards. And per usual, I would like to remind you to keep your microphones muted to avoid any disturbances. And if you have questions, please post them in the chat. Otherwise, we will have a discussion when Andreas is finished presenting. So please, Andreas, take it away. And you're muted now.
Oh, so now you hear me.
Yes, I do.
Yeah. Thanks a lot, Jack. I will start with sharing. There we go. Okay, you all see my presentation?
Yes, it looks great.
Okay, great. So I will talk about this development and research we have done in the area of graphene paper. And so we are both focusing on how it can be produced, so it's production, but also how it can be used, and then optimize properties for this type of applications. Let's see. So what has motivated us? Today, the electron industry is a lot based on silicon. And a lot of this electronics ends up as waste eventually. And this waste is hard to take care of. It's ends up many times in landfills. Let's see, I will put next there. It's a big problem. So could we make the digital future society, could we make it sustainable? Could it be possible to use bio-based sources to make some kind of green electronics? For example, the pulp and paper industry is very good on sustainability in many aspects. Could it be utilized to make electronics? Also, the paper industry has very efficient processes. Materials are very rapidly produced. In electronics, all the electronic actions happens at the surface, and the surface area of a paper is very large. So actually, this is the yearly production of all surfaces in electronics in like 10 years back. That could be produced on 7 hours on a paper machine. So it's you can really scale up electronic production if you can use this type of facilities to produce it. Also, we have new challenges with the renewable energy. So the energy is produced when the sun is shining, when the wind is blowing. In the meantime, it needs to be stored, the grid needs to be supported, and so on. And as we imagine that with using paper production processes, very large scale energy storage devices could be produced that could be incorporated in this renewable energy solution to store energy in a cloudy day or when the wind is not blowing. Another area which is growing very large is the packaging area. And everything becomes digital nowadays. So we want to track what happens to our goods inside the package, what climate they have been, the humidity, temperature, if they have been dropped, what type of pressure forces it's been on the packaging, and so on. or just a simple readout of what is inside the package. Embedding electronics in paper could help with these things. Could graphene paper be part of the solution? Yeah, we think so, and we have set out to evaluate that. So, background to what we have done within the graphene paper. So we mix pulp, cellulose fibers, and graphene, and they are very different, but also very similar. Both is actually very highly anisotropic, so they have a one dimension which is much longer than the other. So they form very nicely form flat ordered materials. However, the graphene doesn't bind so good to itself, and the pulp, we know, forms very nice networks. As we see here also, this shape of the graphene flakes. Let's see, I will show you with a laser pointer. These ones could be very large. It could be tens of micrometers. And the size of the graphene flakes is also good for the to use it in a paper production process. So the big size of the graphene flake would enable physical retention in the paper fiber network when the paper is formed. So it will be rather easily trapped in the paper network. There are other potentials of mixing these two. So with the cellulose fibers, they are easily dispersible in water, so we can use water-based processes. We have this, you can make a rather good control in the material formation, so you can get homogeneous and nice materials. You can also get oriented structures and so on, which is very interesting in electronics. And it forms this robust network. It's a rather cheap material, and it's a very scalable and efficient processes. However, it's not conductive, and it's sensitive to moisture, which could be a drawback, but perhaps also a benefit, especially when you combine it with electronic material. I will not mention it in this presentation, but we have looked into producing moisture sensors of the cellulose electronic materials. So the graphene, it's very highly conductive, both electrical and thermal. So it could both be electrical application, but also how to transport heat in an interesting way. It's extremely stiff. So if you want to increase the modulus of something, it could also be added. It's a good gas barrier, which we have looked into. It will not be touched so much in this talk. It's not sensitive to moisture, so it doesn't influence on that, which could be good, which is a good thing in electronics. It's not dispersible in water, but here a good thing is that together with cellulose, it could be dispersed. So modified cellulose is a very common dispersant for graphene, and also it can be dispersed in other ways and then mixed in water and then mixed with the cellulose. As I mentioned before, the graphene flakes, when they're assembled together, they usually form very brittle networks. So combining it with cellulose, it would increase the robustness of the material. One also needs to consider some health risk here. It has a very sharp edges, the graphene. So one need to consider that when you make materials, because this sharp edges is very lethal for cells and bacteria and so on. So it could kill bad bacteria, but also good ones. So I wanted to take care of that. And it has a tendency to stick to a lot of different surfaces and contaminate processes, equipment, and so on. So to keep track of that. So initially, we did investigations with hand sheet productions, a batch scale process, this investigation we did partly together with Ahlström and Linköping University and Rice Digital System. Here we actually have Patrik Isaksson and Xing Wang here on the picture producing papers in a handsheet format. But simply the process is that we have pulp and graphene or graphite, and then we mix it with some kind of retention polymer, so a polymer that facilitates the graphene to stick to the fibers. We mix it for a while, so we get the homogeneous mixing, and then we dewater it, and upon drying, we get the graphene paper. And then we also investigate pressing, so we get the more high-density graphene paper, and this will increase the contacts of the graphene flakes, and thereby increase the conductivity of the paper, for example. So initially, we looked on how this retention aid functions, and how well we were able to stick the graphene to the cellulose fiber. Here we see a cellulose fiber, which a lot of graphene flakes stuck to it. So chemistry works very well. And here is the chemical retention, so no physical retention here. And normally you want to be between 70 and 90%, depending on your process. So this is a very good value that we can control the retention to this level. So we looked at electrical conductivity. It's not the best looking picture, but here we just show that half of the picture here has been compressed and half is not. So it changed the shape also. It gets more glossy shape when you press it. Here we measure it. This is electrical conductivity, is Siemens per centimeter. And we see that we have some conductivity when we add 20% of graphene, but then at 40, it really starts to increase. And the red bars here is without pressing, so rather low values. And then we see when we then compress the sample, quite highly compressed, several hundred bars, then we reach good conductivity values. We also try to mix in nanocellulose. And nanocellulose helps to disperse the graphene and also form a very homogeneous and nice structure that really bonds the graphene to the paper matrix. However, we saw that the conductivity drops here, since the nanocellulose probably cover the graphene surface and will then reduce graphene connections. So here we see an example of that we looked at how the graphene detached from the paper after they have been formed. So here we take a paper cloth and we swipe it over the graphene paper with a small pressure, and we see here a lot of graphene goes off. And here, this is almost only graphene. It's 90% graphene and rest pulp fiber. So it's quite impressive that we can make a paper with this amount of graphene in. And here we add some part of CNF, and we see that much less graphene goes off the paper, so the cloth is more white. But if we reduce the level of graphene, then it sticks very nicely to the paper network and very little graphene goes out. And I mean, also 50% is a very high level of graphene addition. So hopefully the final product would have less graphene than this, since it is an expensive material. Xing-Wan put a lot of effort into looking at conductivity of graphene on different directions. So here we see as the paper forms normally a sheet-like structure, and pretty much all anisotropic materials form that. So if you have a flat surface and then you have anisotropic materials that lays on the flat surface, it will lay flat. It will not stick up like this. So it's natural that you get a better connection in the plane. And we see that we almost have a factor of 10 increase in conductivity in the plane compared to through the plane. This could be a benefit. It could also be a drawback. So one need to consider this when you look at materials and applications. So to pilot production. So this was batch process. So we were thinking, can we produce the material continuously? We saw a lot of interest, and we talked both research interest and company interest. So we needed to scale up the process. And then we utilized our a pilot paper machine called XBM, which is located at the Moore Research Facility, which is also a part of RISE. And it's a continuous paper machine. which runs at lower speed, 1 to 2 meters per second, and 1 to 2 meters per minute, I think it should be, and it produces grammage like this, and the width of the paper is narrower than normal one. So let's see how it worked. So here we see a graphene pulp slurry coming out, and it forms already at the vacuum section here. It forms a really nice wet web that is possible to be transported through the paper. So here it comes out of the press section into the heat section. So here is the press section, paper goes in there, and here first is the vacuum section. Then it goes into a section with heated cylinders, and at the end of that section, rather dry paper, 80% moisture content something, comes out of the paper machine. And we produce rolls of paper like this. Here we have a reference paper, and then we have two different papers with graphene. These both ones contain 50% with different pulp mixtures. Then we also, as a reference, used carbon black, which is a common carbon source industrially used to make paper black, or for electronic or thermal applications. So we tested this material since it's already industrial. I will talk more about this carbon black later on. I can mention now it was much easier to process the graphene slurries than the carbon black. We also investigated nanocellulose, as I showed in the handsheet productions. It worked very well with the nanocellulose. It binds the structure together. We got a bit drop in connectivity, but like the paper properties improved. However, in a continuous process, as many of you know, the nanocellulose forms these very strong gels and holds water very tightly. So it's tough to bring out the water of the nanocellulose. So we had problem with the dewatering speed. So we couldn't form a strong enough wet web to be able to transport to the press section. So here you could reduce the amount of nanocellulose, use another type, and so on. So this research is to be continued, or some other additive to bond the graphene better to the paper. I was talking about the health concerns. So during this experiment here, we consider that the graphene may dust in handling, especially in the dry end of the process. Dust may start to form. So we used face masks, and we used the right face masks, high quality ones, to stop inhalation of small particles, F3 I think it was. And we also used a special we were spraying the floor with water here. So we were thinking, if the graphene will start to dust, once it falls down to the floor, it will at least stay on the floor if the floor is wet, and we will be locked in the water on the floor. So that precautions we took. That's it. And then regarding handling of the graphene material and cleaning of the equipment, so we had a closed loop of the paper machine, but we have some water going into the head box, some other cleaning waters and so on. So some water that is in connection with the equipment goes out the drain. We cannot circulate everything, but the water that was going out of the drain was almost completely transparent. So we didn't pour any sufficient amount of graphene out the drain. We didn't see any amount really going out the drain. And then at the end of the initial trial, we we collected graphene, the recirculation liquids, in buckets and sent for deconstruction. But we also noted already the first trial that if we had a cleaning pulp, if we produce some paper after the last graphene paper production, the graphene ended up in the paper. So in the second and third pilot trials, we did three trials. Then we had a lot of cleaning pulp, so we collected all the graphene. So here you see the paper is a bit gray, and then the end of this cleaning paper becomes white. So we pretty much collected all the graphene with this cleaning pulp by producing paper in the machine. And with the cleaning, the most challenging part to clean was the press felt. The rest of the machine was quite convenient to clean. You had to clean it accurately and directly after, but then it worked well. In the press felt, we had to clean it. We used regular soap and then brush it. And sometimes we had to clean it several times. So once it dried, you saw, okay, it was still a bit dirty, and we continued. So, but then eventually we got a very clean press felt. So these ones had already been used. So it pretty much looked like this before we ran the process as it did after. This one was cleaned 3 times. So it's possible to clean the machine again. Perhaps one should have press felts that is dedicated for this type of materials. Okay, so what properties did we obtain? So here is some SEM images of the papers. We have to the left, we have a reference without any graphene. You see a normal paper structure. And then we have at 5%, where you can see some, see if I can, yeah, now I can move it. You can see some graphene flakes here and there. You can imagine that here you don't have an interconnected network of the graphene. You have no conductivity. 20%, you start to see more graphene network. So some parts of the structure would have an interconnected network and will start to be conductive. And then at 50%, you see a lot of graphene structure materials. It starts to be harder to see the fiber structures, which are here and there. At 80, it's completely covered with graphene. You see fiber structures here and there. And then here is 50% carbon black. You see it's a totally different structure. It's isotropic material, and they are much smaller. So it's small balls here that are connected together. If we look at the cross sections, we have fiber cross sections here. You see some fiber cross sections. And then we have at the smaller addition levels, you can see some graphene structures here. We actually improved how we made the cross section. So these two above one is cut here with a sharp razor blade, but it's still, you cannot cut the graphene. You just smear it out over the cross section. So here we instead crack the surface in liquid nitrogen, and we get a much better cross section. So you can start to view the structure in the individual components. And you can see some graphene here. Here you see some fiber structure still at 50%, and then it's more graphene. And then here you see carbon black, and perhaps with the carbon black, since it's an isotropic material, you can kind of see a structure going from the top to the bottom. So I can imagine it will be less different in the conductivity through the plane, within the plane compared to through the plane when you use carbon black. So some properties. So first of all, we looked at the carbon content by thermogravimetric analysis. At 550 degrees, all the cellulose were burned off, but the graphene and carbon black had not started to be decomposed. So at that temperature, we took out the mass, and we saw that the mass, these ones, they are almost exactly the levels we wanted. So here we wanted 50%. It's just about 50%, some percent difference. And 20 and 5 and 80, and then for the carbon black we lost a little bit more material. It's harder to retain that, so maybe here we had a 45%, something like that. And we had a combination here as well, which we think are interesting for further evaluation. However, we saw that when we add these particles, we will hinder the fiber-fiber bonding. The graphene particles will be in between the fibers. This one's in between the fibers, and then they will not stick as good. And we lose strength in the material. So the more we add, the lower strength. So actually, this with a 80% graphene, we were not able to roll it up. We could still go through the machine, but we needed to take out sheets in the end. It was too brittle. So this one need to further consider. But however, 20% we see we have very good values. We think that if we optimize the graphene assembly on the fiber surface and in the fiber matrix, the 20 could be a very interesting level for most applications. So we looked at the electrical conductivity, and here it started to be sufficient values at about 50%, and then it increased quite much at 80%. The carbon black, one can see here, has much lower conductivity. So here we measure in the plane. So it's isotropic, less stretched out component, so it doesn't connect as good. But the mixture here showed quite interesting connectivity. And then we see when we pressed it here, several hundred bars, we clearly increased the conductivity. So this one was almost approaching 300 compared to about 50 here. So what could we use the graphene paper for? So the graphene, you can use regular paper conversions of the most graphene quality. You could bend and form boxes, for example. We utilize the electrical properties of the graphene to make a box and electromagnetic shielding box. So if you place your phone inside this box, the phone were not able to be reached. We also made a coffee sleeve demonstrator. So if you take this with a small electrical supply, for example, plugging it into the USB port of your computer, you could keep the coffee warm or even heat it up. So we made a graphene paper here. You see that we covered around the cup, and then we put this on the outside just for it to look good. And then the graphene paper, we had embedded electronics wires in it, conducting wires in it, and we heated it. We applied a 12 volt to these wires, and then it heated the liquid inside. So here we had a hot liquid in, and we see that we could keep the hot liquid at 60 degrees if we have the cup in this conformation, and then we placed the lid on top of the cup, and then it was heated back to about 70 degrees. All right, so that was all for me. And I have been talking today about this, but it's a lot of people that has been involved in this development. So here we focus quite a lot on the scale up, and then I should thank you a lot to Maja Elnerud and to Oskar Westin, which was part of the more facilities in the RISE in Örnsköldsvik, helped me with the pilot machine and the initial development. I've done a lot with Patrik Isaksson, Xing Wang, Carl Håkansson, and then Åsa Blademo and Jon Loftus here have done a lot of laboratory characterization together with Ladan, Karin, and Niklas, Ilja and Sophie, Abbe, and others have also been involved in developing new ideas of how to use the graphene paper. And then from industry, we have utilized in many of this work the material from 2D Fab, and I have had very good discussions with Sven Forsberg from that company about how to use the material and how to best utilize it, and collaborations with KTH and Linköping University and so on. And I'm part of, we are part of a center called Digital Cellulose Center, and some graphene work have been conducted in that center, and we plan to further investigate the use of the graphene paper in this center. So here is more research how it can be done, and then we would like to do more industrial application of it as well. And us that is heading this work is me, Andreas Fall, and also Hjalmar Granberg. So we thank you, both me and Hjalmar, that you have been present here and listen. And if you have any questions or interest in the field, please contact either me or Hjalmar and find our contact information here. Yeah, thank you a lot.
Thank you very much, Andreas. And if you have immediate questions, they are of course welcome now as well. And we have one from the chat, which reads, I suppose stratified forming of paper would be a further improvement of the production of the graphene paper, right?
Yeah, the stratified forming, you could perhaps produce devices already in the paper machine. So you could have conductive layers and then insulating layer and then other conductive layers, and you can form devices, you can form sensors or capacitors or also directly in the paper production. So that would be very interesting to look into.
Very good. You also, so a question coming from myself then, you showed that you have various concentrations of graphene in your different papers, which gave different mechanical properties and electrical properties and so on and so. When you made these demonstrator pieces, which concentrations did you use then?
So in the coffee sleeve we used the 50%, and for the electromagnetic shielding we really needed the high electrical conductivity to achieve that. So there we used 80, I think even we tested even this 90%, but it was hard to handle.
Okay, but it's good that it's somewhat tunable then, and you can have a payoff between mechanical and electrical properties.
Yes, yes.
And I mean, you mentioned both things you have tried application-wise and also possible future applications and such.
Yeah.
Where do you see, or what does the industry think about this? Where's the largest interest?
Yeah, but when we talked with paper producers, for example, Ahlström, that has been involved here, then the key question is really what to use this paper. The paper producer understand that this material can be used in a paper process, graphene, so that's a big thing, and you can find a lot of interesting application, but it also need to be industrial viable, so it has to have the right cost structure and right health aspects and so on. And we currently are in the Digital Cellulose Center. We are interested in investigating further the use of the graphene papers in antennas and also as battery electrodes, but there are many more applications. For some, I mean, the price is they are not so price sensitive, so maybe it's easier to start with such an application. And we also believe that in the end, I mean, it should be possible to get a rather high conductivity, much lower loadings of graphene if you get them perfectly distributed. So that we also work on, you know, how to absorb them to the fibers at the more controlled and oriented structure, so that we can reduce the amount of graphene needed for certain connectivities, and that will open up the possibility for many other more cost-sensitive applications.
So you opened the door to the future somewhat there, but what is going on? What is happening next with this?
I would say that the next things is doing more research on how better assembly of the graphene on the fiber surface, and then looking into these applications where we are investigating if we can look at it at a larger scale, more in industrial scale, like a pilot scale, both at producing the graphene paper, but also the scale of where the antennas are produced. This is a quite scalable material compared to other cellulose electronic materials we are investigating. We are also considering some filtering applications. So this paper have a rather porous structure, and then you press it and it densifies, of course, but you can keep this porous structure for to use it as a filter, and then by heating it could also be antibacterial. You can also kill bacteria and viruses and so on. So it's yeah, so filter is also another application area. Air filters.
I'm seeing a circular loop here. You use the face masks when you produce the material, and then you can produce face masks which can kill bacteria.
Yes, yes. Yeah, maybe towards the end. Now we think maybe, you know, a house or building filters, or so larger units that you're not put on your mouth, but perhaps, and then maybe you use this stratified formation, so you have some normal pulp paper on both sides of the graphene paper, then if you would use it as a face.
And we could maybe see a connection to the webinar yesterday where we used textile fibers to make air filters. But you also mentioned the scalability, and the graphene is a material under development, so to say. The industry is still growing. So what is the source of the graphene here, and how scalable?
Yeah, it's a good, both the scalability and the source. So at the moment, the graphene comes from mines. It's a mining particle that is then it's not a renewable source, but it's a lot of investigation going into producing graphenes from bio-based sources, from cellulose even, but also from others, more carbon-containing ones like lignin, and mixture of the two. So the field is moving to a more sustainable source from which the graphene can be produced from. And regarding the scale, when we started this work, then it was a very exclusive material, and most of the material were very fine. We had 0.5 nanometer in thickness and very large, and it was really an academic material. But now more and more industrial qualities that are not like perfectly according to the definition graphene, but they have a high quantity of graphene, and then also some larger flakes with larger thickness, which could be called nanographite. So here we have used a mixture which contained some tens of percent of particles that are defined as graphene, but it also contains larger flakes, which is more considered as a nanographite, and this particle is then much cheaper to produce. So it's a clear development of the industrial quality of this material. It has been academic materials, but now it's being more and more development to make industrial qualities of graphene. So it goes hand in hand, the development of how to produce materials utilizing the graphene, and also how to produce a graphene quality that is applicable in industry.
Okay, seems like a very good match. Interesting time for graphene paper scientists. So that has still my curiosity, but I'm sure there are more questions from the audience. So you can either raise your voices or post them in the chat. Or If not, which may be the case, you can save your questions and email them to Andreas. You have his email address on the screen, or Hjalmar as well.
Yeah.
And other than that, we thank you very much, Andreas, for this very interesting presentation, and all of you for participating, and hope you have a nice Friday and a nice weekend after that. And thank you very much for taking part.
Thank you, everyone. Bye-bye.
Bye-bye.